Hey there, my name is Henry, and it's my privilege to talk to you about encrypting your communications. Now we're going to start by talking about why you should encrypt your communications, because why would you if you don't understand why it is so important? If we look at modern applications, almost all of them are web applications. That means that the application is running on a web server, like an Azure App Service, and our user uses that application from within their own browser. This means that there is communication going back and forth from the user to the application over the internet, and all that information needs to be securely transferred. When we talk about transferring securely, we mean data privacy. Only the user gets to see the information, nobody else. Data integrity. We know for sure that the data is correctly received. And data authenticity, meaning we can be confident that the data came from the user or from the app service and not from some third party. All these three properties can be provided by encrypting the communication. The most important one is data privacy. Integrity and authenticity are sometimes secondary goals achieved by encryption. Now, I've said encryption a lot of times, but it is important that we both have the same meaning to the word encryption. So when I talk about encryption, I mean a mathematical operation, a rather complex mathematical operation, that has as goal to convert a message, so some data, into a code. That's the encrypted message. And to make that possible, we are going to use a key, which conceptually is the same as the keys you are using for doors and cars. And here comes the thing. It is nearly impossible to retrieve that original message without having that same key. And this property guarantees data privacy. We can also put this in a diagram. We start with an original message, often text, and we're going to add a key. Now both of them go into an encryption operation, delivering us the encrypted text. After encrypting data, you also want to be able to revert that operation. We call that decryption. Decryption has a very similar shape. We start with our encrypted file and the key, combine the two into a decryption operation, which yields the original file we started with. And if you compare the two, you see they are very similar, just the operation is different. Now, expanding a little bit on the drawing that we started with, it is important to understand that in a modern application there is more communication going on than you might think at first sight. For example, let's assume we have this same user working with the app service we talked about before. But that app service actually stores all its data in a SQL database. It has some configuration that it loads from an Azure App Configuration instance. And finally, it generates a lot of logging information, which it stores in application insights. If we look at this architecture, you will see that all these components are deployed independently, meaning on different servers, or containers, or whatever. The essence is that there are 4 communication lines in this architecture, not just one. And all 4 of them should be encrypted. Because encryption is nowadays expected as a default. Just go to any website using HTTP instead of HTTPS and your browser will probably stop you, saying, hey, this is insecure. Encryption is becoming a default. That encryption can be either when the data is at rest, when it's in a database or stored in a file on a server. It can be encrypted in transit, when you're communicating that data, which is what we will cover in this course. But it can even be encrypted when in use. This is much newer and there is still a lot of research going on in this area. But all 3 properties are important to consider. Now, even when your users or your product owner doesn't ask you about encryption, keep in mind that many compliance standards, like ISO 27001, HIPAA, or GDPR, require you to encrypt all the data you are communicating back and forth. I hope you now agree with me that encrypting all your communications is very important. And join me in the next lesson to talk about what is not encryption. Now, before we continue our conversation about encryption, we have to talk for a very short while about hashing. Hashing is not encryption. It is a different thing, but is very often confused with encryption. So let's put the two of them side by side. As you know, encryption is a mathematical conversion of data into a code which is nearly impossible to revert without the key that is used for the encryption. Hashing is also a mathematical conversion of data into a code, but now in a way that is completely impossible to revert. But it is very repeatable and doesn't include a key. So what you know about encryption is that we combine an original text and a key in an encryption operation to create an encrypted text. Hashing is a little bit different. Here we have only our original text, put that into a hashing operation, which yields a hash. And it is impossible to go from that hash back to the original text. To apply that on an example, one possible algorithm for hashing is SHA-256. If we would apply this algorithm on the text hello, it would return the string you see on the screen. Now, one of the things about hashing is that the outcome, which is called the hash, has always the same length. So if I would put in a much larger text, it would still have the same length. What's also cool about hashing is that changing just one letter in the input will completely change the output. So there is really no way back from the output to the original text. The most common use case for hashing is around validating passwords. If you apply hashing, you can store the hash of a user password, which allow you to validate a user's password without having to retain the original password, which is a neat feature of hashing. However, if you ever hear somebody say, "Hey, I encrypted this using hashing," now you know that's not a thing. Alright, I hope to see you in the next lesson, where we will continue talking about real encryption. There are many ways you can encrypt information, but generally speaking, there are two distinct approaches: symmetric and asymmetric encryption. When you're using symmetric encryption, you are using one key, and that same key is used for both encrypting and decrypting the information. When you're using asymmetric encryption, you are using two different keys, one for encrypting the information and one for decrypting the information. Now, don't make the mistake of thinking that there are just two ways you can encrypt, asymmetric or symmetric. There are actually tens or hundreds of algorithms that you can use to encrypt information. They just fall into these two categories. Now, to make things just a little bit more concrete, let's go over an example of symmetric encryption. Let's say we want to encrypt the string hello. Now, as encryption is a mathematical operation, it works much better on numbers. So let's transform this into a series of numbers. And I'm using the approach where A equals 1, B equals 2, etc. We're also going to need a key. Let's call it my key. We're also going to convert this into a series of numbers. And now comes the encryption part. We're going to add the numbers together, and then we're going to correct them to be between 1 and 26. This final series of numbers we can transform back into a series of letters. And now we have our encrypted text. Now to decrypt this, let's move that text up there, transform it back into numbers, do the same for our code as we just saw. And now instead of adding the numbers, let's subtract them. We're now getting two negative numbers, so we're going to add 26 to correct them so that we can transform those back into letters. And hey, that's our original text again. This is a very simple example of symmetric encryption and decryption. And the algorithm that I showed you right here is called a Caesar cipher, which is a type of additive cipher falling in the category of symmetric encryption. If you want to apply asymmetric encryption, you're going to start by generating a full key. And then split that key into two parts. The first part we call the private key, and the second part we call the public key. Now that private key is used for decrypting messages sent to you. The public key, which you use for encryption, can be shared with everyone, because everyone who has that public key can send encrypted messages to the holder of the private key. In the examples of encryption you saw before, I always assumed symmetric encryption. If we were to draw a diagram for asymmetric encryption, it would look like this. We have our original text and the public key, and we combine these two into an encryption operating, yielding the encrypted text, the code. We can then take our private key and combine that with the code into a decryption operation, yielding us the original text again. I'm going to attach a PDF to this video that helps you practice with this on your own computer. Now it's important to understand that asymmetric encryption is much more demanding on compute, so on CPU. That's not necessarily a problem when you are using a browser to go to a server, but if you are a server and you have to serve thousands of users, that is a thing to keep in mind. Asymmetric encryption is used for signing data, a thing we will not talk about in this course. But you can also use it to encrypt messages or records that are being transmitted over an insecure channel. For example, I can encrypt a message, give it to somebody I don't trust, who then gives it to the receiver of the message, who can decrypt it, and we still have secure communication. The other use case for asymmetric encryption is to establish a secure channel, for example, over the internet. Now there are a number of ways you can do this, and this is just an example. Let's assume we have two parties, traditionally called Alice and Bob. Now Alice and Bob want to establish a secure channel between the two of them, and to do that they need a shared secret, a shared key to use for symmetric encryption. To build such a key, they first agree upon a starting key, and that can be completely public and in the open, nothing secret about it. Now, independently from each other, Bob and Alice both apply encryption using their own private key to that pre-shared public key. They then exchange the outcome of that operation, and to the thing they received from the other side, they again apply their own key. Both Alice and Bob now end up with the same key. Yes, the encryption with the key and Alice and Bob is in a different order at both sides, but that's not a problem, because the order of encryption doesn't matter. So that's the difference between symmetric and asymmetric encryption. And as you just saw in this example, there are things that you can do with asymmetric encryption that you cannot do with symmetric encryption. Now let's meet in the next lesson, where we will talk about how you can use these theories to encrypt your communications. Now let's talk about how we can use all of this to encrypt the communications between two parties. When we're talking about communication encryption, there is a very important distinction between two types we have to keep in mind. The first one is end-to-end encryption. This means that there is a single secure channel from source to target, and messages are never decrypted in between. We can also have per-connection encryption. This means that messages are sent from source to target over a number of hops, and while the connection between hops is encrypted, information is decrypted and re-encrypted at the different hops. Now this distinction is important, because using per-connection encryption can open you up to man-in-the-middle attacks. Let's assume Alice and Bob are communicating and they want to do that securely, but there is a system in the middle to which Alice sends encrypted messages. That system decrypts the messages and then re-encrypts them before sending them to Bob. When this system in the middle is compromised, messages between Alice and Bob can be intercepted on that system. Now that's not necessarily a problem per se. For example, many companies use this approach to inspect traffic coming into their network or going out of their network. But it is a very important thing to keep in mind. If you don't use end-to-end encryption, you can be open to man-in-the-middle attacks. When we talk about encrypted channels, there are quite a few different protocols you can use. The most common one is HTTPS, so not HTTP. It is basic HTTP over a secure channel. And way in the past, that was called SSL, Secure Socket Layer. We don't use SSL anymore. And when sometimes people still talk about an SSL connection, let's just hope they mean TLS, because TLS is the successor of SSL, and Transport Layer Security is now the protocol we use as part of HTTPS. Now, as with many security protocols, newer versions keep coming out to keep guarding us against newer and more sophisticated attacks. As it stands right now, use TLS 1.2 or higher, and if you can, use 1.3. Another well-known protocol is SSH. This originates from Linux systems, where SSH is the protocol used to establish a secure terminal on a computer on the other end of a network. VPN is a protocol that you can use to build an encrypted network tunnel between two hosts. VPN is frequently used to build a secure connection between two servers that are connected over the internet. VPN then provides a virtual, secure network connection between the two of them. And finally, we have FTPS and SFTP. These are two encrypted variations of the file transfer protocol. So if you want to transfer files, don't use FTP, but use FTPS or SFTP. Now this list is not complete, but these are some of the protocols that you are most likely to encounter. Now please join me in the next lesson, where we will see how you can apply these to your own architectures. Now let's talk about how you can apply all of this when you want to encrypt the communications going on in your own architectures. In general, I would recommend you to start going over your architecture and identify all the lines of communication. For example, if you have a web application, there are users accessing your application over the internet. But that application might also access one or more file shares, have a configuration sitting somewhere on another server in Azure, and maybe it has to fetch files from a legacy server in your own network. So there are a number of communication lines that we have identified, and we can go over them one by one to talk about how we can secure them. If we start with accessing the file share, we can use the SMB protocol for this, which is a secure protocol. If you use version 3.0 or higher, but preferably version 3.1.1. The communication from the user to the app service and from the app service to the app configuration can be done over HTTPS. So here we have to make sure that we're not using SSL, but TLS 1.2 or higher, and if we can, 1.3. That leaves us with the communication from our app service to the legacy server. And we're in a bit of a pickle here, because the protocol that we have to use is FTP. Ideally, you want to switch to FTPS or SFTP, but that legacy server just doesn't support it. In situations like this, you can fall back on another solution. If we can't use an encrypted protocol, we can encrypt the network connection from the app server to the legacy server. And to do this, we can use VPN. This way we are first establishing a secure channel from the app service to the legacy server, allowing us to use an insecure protocol and still being sure that nobody can intercept the traffic. Not a thing to do by default, but a great way around insecure protocols. Once you have done this exercise and you're starting to encrypt the connections from and to your applications, there are just a few other pointers I want to give you. The first one is you should consider writing an end-to-end test that constantly verifies if the communications from your application to other sources are still encrypted. I mean, if you lose encryption, everything will still work, so you're not notified by a user or an alert going off. Instead, regularly testing that the encryption is still there can help you prevent unwanted consequences. Another thing that you might consider is writing your own encryption algorithms. I have a short advice. Don't. encryption is complicated. Instead, you should look at the industry and find an existing library that provides you with the encryption capabilities that you need. Now, if you're going to apply encryption to an existing architecture, make sure you consider the performance implications of adding that encryption to an existing communication channel. Encryption, and in particular asymmetric encryption, requires a lot of CPU or GPU power, so make sure your server has that available before releasing this to production. I hope this gives you some pointers on how to get started with encrypting the communications from and to your applications. Now please join me in the next lesson, where we will wrap this course up. Well done, you have completed another lesson. And the one question remaining is, of course, what to learn next. So please allow me to give you some options on what you can do next. If you want to dive deeper into security in general, you might want to take a look at Data Security Champion Data Encryption by Kevin. Or as an alternative, Introduction to Data Encryption, an AWS provided course. If you want to take a deeper look specifically at encryption, you might consider Analyzing and Decrypting TLS with Wireshark by Ross. In this course, you will get a deeper understanding of how TLS works and how you can use it to secure HTTP traffic. Another option is Secure Coding in ASP.NET Core, a course by Gavin. In this course, you will focus on how to secure the communication from your user to your web application. But of course, there are materials available outside of Pluralsight as well. If you want to get hands-on with encryption, I want to encourage you to take a look at Bouncy Castle, an encryption library that's available for both C# and Java. If you want to dive deeper into how asymmetric encryption works, you might want to take a look at RSA, one of the most used algorithms for asymmetric encryption. There is a description available on Wikipedia, but there is also one available on geeksforgeeks.org. Here you don't just find an explanation of how the algorithm works, but there are also code samples that allow you to get a bit more hands-on.